So the final part of this problem is to see if the cable and the support can handle the load. So the first thing we do is draw the location of our center of gravity, and that's simply where the weight acts. If you remember, this is the mg, the total mass times g, and this is the location of the center of gravity. Now, this is a free body diagram. We resolve the tension into two components. The component next to the angle is cosine of that angle. The component that's far away from the angle is the sine of the angle. That's an easy way to remember how to resolve a force at an angle. And down here we have two reactions, Rx and Ry. Now, let's start by taking a moments equation, and I'm going to take moments about point A, support A. So what we say is, we say the sum of moments, always pick anti-clockwise as positive, about point A is equal to 0. The sum of moments is equal to 0 because the system is in equilibrium, it's not moving. Now, let's start with the first force. Now, I'm going to start with TA cosine 30, this force here. So it's going to be force multiplied by perpendicular distance to the pivot. So force multiplied by perpendicular distance to the pivot. This distance here is 1. So my first term is going to be TA cosine 30 all multiplied by 1. And we can clearly see that it's anti-clockwise because this force about this pivot will make it spin like this. So anti-clockwise is positive. Now, plus our next term. The next term I'm going to go for is TA sine 30, which is this component here. So again, force, extend the force, force times perpendicular distance to the pivot. So it's distance from here to the end of the body. Now, this is 1, this is 0.3, so it's going to be 1.3. Again, this is also anti-clockwise, around the pivot, anti-clockwise. So plus TA sine 30 multiplied by 1.3. Finally, we have plus, we have the weight. Now, the weight, if we see it here, is force multiplied by perpendicular distance to the pivot. That distance is our x bar, which is 1.15. So this force times pivot, this is going to have a clockwise turning effect because it's going down. The pivot is here, so it's going to be clockwise like this, so it's going to be negative. So minus mg, which is 394.45 G, 394.45 G, multiplied by x bar, which is going to be 1.15, all equal to 0. The sum of moments is equal to 0. Now, if we expand this, we're going to have root 3 over 2 TA, that's cosine 30 times 1 is root 3 over 2, plus sine 30 times 1.3 is 9 over 5, so 9 over 5 TA. Now let's move the last term to the other side to make it positive, is equal to 4444.9. That's when you expand that right term. Now take TA as a common factor, so we're going to have TA, open bracket, root 3 over 2 plus 9 over 5 is equal to 4444.9. Now, to find TA, we simply divide both sides by what's inside the bracket, and we have a TA value of 1671 newtons. So this is smaller than the maximum permissible tensile strength of the cable, which, if you recall in the problem, was 2.5 kilonewtons or 2,500 newtons. So therefore, the cable shall not fail. Now, let's move on and find the forces at the reactions. So we could take moments again, but an easier way is to take the sum of forces. the sum of forces in any direction is equal to 0 because the system is in equilibrium. Let's start by picking the y direction. I'm going to pick up as positive, forces about y, forces in the y direction should I say. Now, in the y direction we have three forces. We have TA sine 30, that's the first force, acting upwards, so it's positive, plus Ry, which is also acting upwards, positive, minus mg, which is acting downwards, 394.45g is equal to 0. Now we have TA, we've just found TA in the last problem, so let's substitute 1671 sine 30 minus 394.45g, move Ry to the other side equals minus Ry. Now we're going to find Ry. From this calculation, we find out that Ry is in fact equal to 3034 newtons. There we go. Now, final thing, let's find x. The sum of forces in x equals 0. Let's pick right as positive. It doesn't matter with these, with the x or the y, because there's no acceleration. So pick any direction as positive, it's fine. Now, to the right we have Rx minus to the left TA cosine 30 is equal to 0. Again, substitute and rearrange. Move TA cosine 30 to the right side. It's going to be Rx is equal to, we have TA already, 1671 cosine 30. In the end, you should get an Rx value of 1447.1 newtons. Now, there's two reactions at support A, so we have to find the resultant reaction, which is using Pythagoras, and I've shown a picture here to illustrate it. We have Rx, we have Ry, so they have a resultant which acts at an angle. Now, this resultant can be calculated by using Pythagoras. So we can do this here. R is equal to the square root of Rx squared plus Ry squared, which is equal to the square root of Rx, which is 1447.1 squared, plus Ry, which is 3034 squared. This will give you a resultant value of 3361.4 newtons. This is less than the 4 kilonewton maximum that this support can hold, so therefore the support shall not fail. Now to find the angle, we simply apply tan, so angle theta, or we could say tan theta, is opposite over adjacent. The opposite here is going to be, as you can clearly see from here, opposite, which is going to be the same as that side there. That is the same as that. Ry over Rx, Rx being the adjacent. Ry over Rx. Substitute your values of Ry and Rx, do inverse tan, and it gives you theta is equal to 64.5 degrees. Even though the problem didn't ask for that, we're going to calculate it anyway. So that is the final solution to this problem.